Okay, you should be better now. So I'm not sure if you can see me right now because I've got the camera pointing the other way to make it a little bit easier. Seems like we
Yes.
can't change the camera direction at the same time. And if everyone's wondering why I'm wearing sunglasses indoors, it's because these are my Meta glasses. And I forgot to bring earbuds, and the audio quality on these glasses is exceptional. So I'm using them as my audio link. So basically, like I said, here we are. We're at Automate, and let's go take a walk. And what you're going to see is a great collection of industrial robots in one place. And right in the center here is where they have all the major robot brands. We're going to see lots of different ones. There are robots everywhere. Even the small booths have little robots now because cobots are just so ubiquitous. And you'll see like the same brands kind of showing up in different places like Shook. They basically make end of arm tooling. And again, I keep on saying that, the business end of the robot is the hand, or the end of arm tooling, as they call it, EOATs or grippers or end effectors or whatever you want to have. And Shunk is like the ones that make those things that go on different robots. In this case, they're showing what's usually referred to as Big Yellow or Fennec, but they could be going on a Kuka or Stoibli or Scala or any other brand. But what was interesting here is to see some of the different types of kinematics. And I'm going to first head over to this other booth here. You can see the halo over there for Kawasaki. And they brought the biggest robot that's here. And you can start to see it right now. You see that big screen display that's being held up by a robot? Okay, that's the Kawasaki robot. And it's got a rather interesting kinematic. And the one thing that drew my eye to it is, remember the other day we were talking about linear versus rotary drives. And I pretty much said that modern day robots don't use linear drives anymore. They do everything rotary. And so it's kind of surprised to see here's a modern day robot that is using ball screw drives.
It's huge, huh? Huge robot.
Yeah, so it's pretty big. So this is able to do 1,500 kilograms. So it's a very heavy payload class. And because of that, you have to have a unique kinematic design to be able to handle it. Now, at the same time, they have extreme accuracy. I think they said they had like 0.2 millimeters of accuracy or repeatability out of this, which is just outstanding for any robot, especially one of this size. So there's a couple of things I want to point out about it. In some ways, it's an articulated arm. It's very similar to that. And if you look down on the base, that's basically joint one. I think you're going to see a motor there and another motor on the other side. So this robot is so big that one servo is not big enough. So you have one there and then one that we're seeing coming in the front of our view right there. So just axis one alone has two servos. Now, if you look in the center there, you're going to see there's two motors stacked right there in the ball screw drive. In the ball screw drive is this linear drive, which is basically taking this parallelogram there and using it to be able to change axis two. Now, the thing about a parallelogram is it's unstable, right? Unless you lock one of the joints. So if you were to build a freestanding parallelogram, it would fall apart unless you lock one of the joints. And what that ball screw is doing, and we can kind of see the nut that's on the ball screw that's connected to that length there of the parallelogram. As the distance of that moves going back and forth. Okay. Oh, we got an e-stop here. We got to be careful here. So you see all those little sensors there to make sure people like me don't get too close to the robot and do something stupid. So, um, so you look there on that parallelogram, and as that thing moves, it causes it to articulate about the second axis right about there. All right. And the rest of these kind of move on their own to keep that structure. That very rigid structure makes sure you can kind of move it. And it's more efficient to do that when you have a really heavy payload than trying to put a motor directly on there. So this was a very 1980s solution to even smaller robots back in the day because the actuators just didn't have enough rotational energy in the time. But eventually the servos advanced enough that they were just going direct there. So this is a rare example of you seeing a robot with a ball screw drive. And it doesn't just have one, it's got one up there too. So if we look at the third axis, it's also doing the same trick, but in this case, rather than being a parallelogram, it is a triangular kind of structure. Now, when you get out to the wrist, which is already a beast, you can see the servos that are kind of sitting up there that control that. So they're standing them off so the payload of those servos is not something else you also have to carry. that's the other idea sometimes of putting the axes for like down lower in a way to make sure you're not carrying that payload if there's another way. And that's usually what these parallelogram structures were about, is like a trick of being able to get the servo of the third axis down at the base where it's much easier to carry moving around. So this is a giant robot. It's the biggest one here. Now, Fennec has a huge bot, but they didn't bring it. Usually they'll probably be at the Automatica show, and that robot is called Godzilla. You may have seen it in like some of the Tesla gigafactories where it's able to pick up a whole car body and lift it literally up to another story to bring it from a lower conveyor up to another. So you would need something like 1,500 kilograms to be able to do that in a very large envelope. But if we look around at some of the other robots, this will be the last example of that. But we'll see, here's another robot that's, it's kind of a high payload kind of thing, because in a palletizing case, you might have to be carrying very heavy boxes around. We can see they also use that backlink solution. You'll also see that they have some dampers on there, which act as basically like a counterbalance. And then you can kind of see where the motors are. So you see there's no motor up high because the Axis 3 motor is actually down low here, moving that basically parallelogram kind of structure along there, along with this other fancy linkage, because in this case, it's really kind of a four-axis problem palletizing. So it naturally keeps that wrist. So the wrist only has really 1 degree of freedom there for rotating. The other motion you see in the wrist, which would typically be like the axis 5 on most robots, it's actually connected through that parallelogram structure. There is no motor there. It the mechanics guarantees that the thing always stays horizontal. You don't need a motor to do it.
It's very
That's
interesting
that's the
design.
control.
Very interesting design. The first time to see something like that. This
Oh
kind of.
yeah, yeah. So it's very typical in palletizing to be able to see that, where you have really heavy boxes that you want to move around at high speed, and also be able to carry. Now you see that little trick that they do there. Um, they're just picking up the boxes, but they're not sure about the precise location of the box. When you put it over here, a lot of times they have this trick where they draw, sometimes it's called like a gravity table. In this case, they push it in there, but sometimes you'll like drop a part that slides down and forces it into a corner. And now the position of that box is well known. You know, you see, it's not quite there. We push it in. It's now I can confidently drop it off over there because now I know where I'm gripping it more confidently. So that's like that's an elegant trick. I mean, it's a simple little trick to do that to make sure the location is good.
So to understand
And
the table in the middle is just for calibration,
yep.
basically. Calibration.
Yeah, well, what all the table, it's a calibration. So you see how it pushes it in, because I'm not confident where those boxes are. The pallet was dropped wherever, and maybe the vision system is picking up, or the pallet is supposed to be within a certain thing, and now it makes sure all the boxes are packed in nice and tight, and you can get it to where you need it to be. So you can confidently drop it off because this robot's running blind. It's being told that there's this many boxes and it's this pattern. This is how you pull them off. So, and as you can see, it moves around pretty quick. Now, if you look at these industrial robots, you'll see that robot that we were just kind of looking at. Again, you'll see some counterbalances on the side. It has a lot of sharp edges on it. It's really rough, a lot of metal, sharp edges, corners, and stuff like that. Same thing with this one. You don't want to be anywhere near these things. Now, there's the other robots, which are cobots. This is a cobot. You can be near the cobot for many reasons. Partly, it's a lot softer and smoother. You see, there's no sharp edges on there. Now, I'm actually surprised that they're allowing this thing to be run without safety fencing, because I'm not sure that's necessarily cobotic certified. And again, there's a big pinch point right there. I don't want to get my hand in there because that's a pinch point. But if we look over at a cobot here, okay, this one still has a similar type of wrist. We're going to see how the cobots are designed to make sure you don't have a pinch point like that. So this is almost 100% cobotic, but not quite. But if we come over to the Fanuc booth, and the big thing that Fanuc has done, let's say when cobots first came out, it was small upcoming companies like Universal that did it. And the big manufacturers did not build cobots at first, or they licensed them from other manufacturers. Well, now if you look up there, you see Fanuc has gone all in on the cobots. So that's the big thing that they're showing. They don't care about their big beast. And we can get an idea of what's going on with cobots. The cobots are doing heavier payloads now. And compare the wrist. The wrist of that yellow robot over there, you see the pinch point on axis 5? You see the offset here? There is no place I can get my finger caught in there. And again, it's very soft. these things are designed to not move very fast, or if they are moving fast, it's because you've got some sort of safeties around here that's able to detect there's no one nearby. If there's someone nearby, they will slow down or they will stop, one or the other. But and the cobots are even getting better. And again, look at that wrist. That wrist is designed. There is no pinch point like what you would see in a traditional robot arm. And let's see if we can find a traditional robot arm again around here to compare it to. And not, you see, they're just going all in on the cobots. So this was typically a space reserved for your industrial robots, your standard IRs, and as you see, the cobotic form factor is taking over more and more, doing you know, all sorts of applications you never would have thought of before. And yeah, so let's kind of move on and take a look at some of the others and examples of heavy payload robots over here at ABB.
Are they
Mhm.
selling this robot? Are they selling this robot array for sale or just to like
Oh
the?
yeah, yeah, they're for sale. Yeah, I mean, if you want to buy one, we can. I don't think I have the budget, but yeah, we could. So now you have ABB also has their offerings here, of different cobotic arms, and then your more traditional industrial robots. So this is one of their heavier payload robots, as we can see right there. You know, they're doing that one all with rotary axes. And this is a press tending robot. This is an 11 degree of freedom robot that's for picking up the sheet metal parts that come out of the stamping plant and move it from one press to the other. And it can move pretty darn quick. And you see, it's a 6-axis robot with a 5-axis end of arm tooling completely integrated in for 11 degrees of freedom. And you'll see the counterbalance in the back. So you have a parallelogram again. You'll see on both sides of the robot, there are servo axis. One servo axis is directly tied into axis 2 to move it. And you'll see axis 3 up at the top, there is no servo there to make it rotate. It's because that parallelogram does it. And at the bottom of the parallelogram, you have a very heavy mass at the back. That's the counterbalance. So when that robot is stretched way, 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 way out, that counterbalance will help keep the payload from being too heavy. They do the same thing in elevators, right? You have these weights in an elevator so that all the elevator has to do is lift the weight of you and not the carriage itself. And that's sort of the same idea. And so again, a mass is brought down lower. The third axis is a little bit lower, and it just has better overall properties for being able to control that upper axis. But look how big that wrist has to be, and it's a pretty big, heavy payload. Other robots here that you're going to see, no linear drives. I mean, we're not going to find any linear drives, certainly not in the smaller robots, and you're only going to see it in that ginormous robot that we were just at. So that's an example.
Did you find any linear? Did you find any linear actuators?
I
Did you
mean,
find any?
you will find linear actuators for linear applications, or for like a Cartesian robot or something like. Okay, so here's an example. This is a Cartesian robot. And of course, all the actuators there are going to be linear in one way or another. Also, notice what you have to deal with cabling. What do we do with the cables? So you have these what they call energy trays here that allows you to route the cables through it. Anyone has a 3D printer at home? You've seen this already. You've got something like that. But the same idea, you get a linear axis. If we want to find a linear axis in a robot around here, okay, so here's an example of a UR robot, and we can make it over to the UR lab or the UR stand in just a second. They're around here somewhere. Um, and let's see, I got myself a little bit lost moving around. Oh, yeah, they're over here along with some other cool bots. Oh, we can take a walk through the KUKA booth, which is going to be coming up once we get, I'm around a putting green. I don't want to be walking on a putting green. Um, and there's also some servo suppliers here, people who are selling different kinds of drive units, linear drives and rotary drives. Some of them they're hoping will go into humanoid bots. Okay, here's an example of a robot with a turntable, and you see the problem is that you get something going on at the end here, and you got to get your cabling and everything around there, and sometimes you have to come up with a really interesting mechanism to be able to route the cables without it getting in the way. But you can see the 6-axis robot that's there, and you've got what is probably a 2-axis turntable, and that allows you to position the drum in the orientation that you need to do gravity welding. So the whole idea is that you prefer to always weld with a torch facing down with gravity and not have to go on the side. So you add an additional axis. Technically, this is an 8-axis robot. Six plus 2 positional axis on the table. So that's one kind of solution. And then I don't think, I'm not sure if KUKA has their biggest robot. KUKA also sells um, AMRs as well. They're kind of famous for some heavy payload ones there. Oh, we got a couple of different arms here. These are their kind of medium payload kind of arms that you'll see. Again, look how skinny that robot is. Everything is being done with rotary actuators. No need for linear drive anywhere. And okay, usually when okay, so that's the foundry version of the robot. Usually the black Kuka robots that I've seen are actually used in movie productions where they carry cameras around, and you don't want lighting, to be reflecting off of the robot, so they intentionally paint them flat black. Let's see if we can find. I'm going to see if I can find a Scara robot around here somewhere. Okay, this is Universal Robots. They are the ones that basically invented the cobot. So you can thank them for that. And so you can see some of the classic industrial. Now, these are upscaled. So these are kind of like the newer versions they have that are slightly heavier payload, trimmed a little bit different than the original ones. And I think somewhere around here we'll kind of find the original. Yeah, here we go. These are more the original classic Universal Robots that everyone is used to. Again, the wrist is designed in a way there's no pinch points on there. And AMRs. And I know someone around here who's going to have a Scara robot. I walked past a bunch of them a few minutes ago, and now I can't remember where they are. Now, again, Universal is so ubiquitous that some other booth here decides to use them as the arm to display their product. Same thing with Fanuc. They'll show up everywhere, or Kuka will show up in someone else's booth. So you have lots and lots of different suppliers of these bots. And I am sure I will find a Scara robot. Whoops. Yeah, I got to be careful about that. See, it's marked for people like me, and even then I still tripped. Uh, so I have to, oh, okay, here we go. So here we go. Your classic Epson, your small Epson tabletop robot. It's a 6-axis articulated arm, but Epson is actually more famous for this kind of arm. And this is a Scara arm. So here's an example of a robot with a linear drive, all right? So you have 3 rotational axes, the first 2 in the middle. And in many ways, you can consider this a cylindrical robot. Really think of it as a cylindrical robot, but rather than having a telescoping radial arm, you have those 2 arms there where the elbow basically controls the distance from the first axis out to where you want to be. And then you have that quill, which goes up and down, and it can also rotate. So that's how you get your four axes. This works in a plane. It's designed to work only in a plane, but it's a very, very fast robot, and it's a very stiff robot. So it's great for high precision, high speed. They're so fast and so precise that typically they put chips on boards. They're designed to be able to do that. They can just go over and pick them up, and they'll go around. And right now, I mean, it's not showing off its speed. These things are incredibly fast. Yes, easily, yeah, easily. And when it decides to go, okay, now it's deciding to go. It's pretty quick. And the G's on these things, this can pull a lot of G's when it accelerates, when it really decides to do something. Yeah, yeah, yeah. It's very fast. Exactly, exactly. And there's different versions of Scaras, but that's the basic concept. Just and then here's your other kind of you know classic kind of robots that are going around here that will provide different precision. And small desktop robots. And again, the comparison is that they softened the edges on this, and it's probably slow enough, but you do have that classic form there where you've got a central wrist that is not offset, but does present a potential pinch hazard around humans. Whereas when you go back over to this design, they get away from it, but you do have an offset wrist, which is a little bit, sometimes makes accessibility to locations a bit tricky and a bit difficult. Oh, here's another company we'll probably be keeping an eye on that's out of Cologne in Germany, Igis. They just announced the Iggy bot. So you remember Iggy? It's also another humanoid bot entry. And the actual arm of Iggy is this one right here. So I believe this is a 6-axis arm. So they're using basically their cobotic arm, mounting it onto a torso. And not only do they make arms, they also make AMRs. Okay, so there's a mobile base. So what they did to come up with Iggy is they said, we're going to have it walk around on this. We're going to build a torso. We're going to put a head on it. And I'm going to take the arm we already have and bring it on over there. Now, this is an interesting, this is a delta. If you've ever seen a delta, again, it kind of competes with a Scara for speed and precision. It has a slightly different or bigger workspace than some Scaras, and it's very, very light. Those are carbon fiber arms that are on there. And remember, we always are talking about like Heim joints and stuff like that. This thing is full of Heim joints, and you have three rotational axes up there that are 120 degrees apart that go down there, and they move this weird mechanism that's tied to that platform down there. And because of the mechanics of that, that platform stays horizontal. That central axis is coming down there. It doesn't need to be there for the platform to be stable. The only reason it's there is it's designed to drive the rotational axis that's at the very end. So the position is done with these three axes, and this is a parallel kinematic mechanism. The idea is that all of your servo mass is up at the base. It never moves. You're never moving them. And you have really light arms that's able to move that lower platform at exceptional speed. The thing about this is it's got a really big workspace in the X and the Y, not so big in the Z. So it's a really big kind of flat cylinder that you're able to do. So it's mostly kind of like a 2D problem where the Z is just to get out of the way and hop over something that you might be moving around. Applications where you see this will be like putting chocolates into boxes that are just coming down the conveyor line, and it goes over, picks up a chocolate, which is very light, and can precisely and quickly drop it into the correct location on a box. So that's one kind of example that you might see that. And sometimes you may not need the rotation, but if you do, that's one way. And it's a little tricky to see, but you might see that there is kind of a cardan joint right at the center there, which is the ability of that, because the rotation of that axis, that's the fourth axis up there. You see the axis is hanging up at the top of the structure there? And then you get this weird kind of telescoping thing. If you'll notice, that whole structure is able to rotate. And it's the rotation of that that allows the very end down there where the green suction cup is. They want that whole thing to rotate because, again, I'm making like Valentine chocolates, right? And I pick up a heart. The heart's going to be rotated in the right orientation to be dropped in the box. If I'm just dropping round chocolates in there, I don't need the fourth axis. But because the chocolates are coming out of wherever they do in a random orientation, this thing has to pick it. And usually there'll be a vision camera around there looking at the prey that you want it to pick up. And it says that one there, it knows how fast the conveyor is. It tracks it, goes down, grabs it, picks it up, brings it over, drops it off where it's supposed to go. So those are very high speed Delta bots. Again, okay, here's a linear axis. An example, whoa, that's pretty fast. I think you just saw how quickly that goes. But these cable trays, these are very necessary things because somehow you've got to get all your power and services from the ground out to the very end. And you need to come up with these energy trays or cable trays they talk about. So we can see how quickly that works. And you might mount like a little robot on top of it to extend the work envelope of your robot. Um, yeah, yeah. So yeah, yeah. And again, so they have some of their different cobots here. So again, this is Igus out of Germany in Cologne, and putting together another Cartesian robot. And then again, the arm that's going to be, and we can see a little bit of close-ups of some of the servo drives that they have to be able to put. Now, the one thing I'll say about this arm is the entire controller for this arm is right there. It's in the base of the arm. There's nothing else after that. You just plug into power. Maybe you connect to like Ethernet services or something like that to tell it what to do. But everything is in there. There's no big box controller somewhere else that goes through here. Because if we look at a standard robot, let me see if we can come over to these robots here. Okay, so this particular arm here, uh, you see that big box right there, that big gray box, and the teach pendant that goes in front of it, and the e-stop, and all those things there. That is the box that is telling this thing what to do. So you see all the cables come out of that box, going over to there, and then it works. Now I had to be very careful here. Hopefully I didn't throw my fingers too close. You'll see that there's a light curtain right in along here. If I attempt to walk in there, that robot will shut down right away. So that's the idea of these safeties. So all these are here, and then someone's going to have to go here and do a reset. Looks like me. I wonder if I accidentally, see, I get too close with my finger poking there. You know what they say? No finger poking und mitten graben and everything, and uh, make sure you kind of stay away. I think I had. Okay, one of them will figure out. You know, that's what they're trying to show off here is more as a robo fence in the application is how a dummy like me can go ahead and imagine to shut the whole thing down. So, yeah. So that's like an example. So what you done? Yeah, there we go. See, he said you just proved how your stuff works, right? Exactly. So it does, so do you see? I barely broke that curtain. I wasn't even aware that I was going through it, and it made sure to come to a stop. So okay, make sure you know what you're doing and stay out of the way. And here's the big controller. So yeah, you basically go through. I had an idea what to do, but you know, don't touch someone else's equipment. So you're taking that big controller there and you're scaling it down and it fits in the base of that arm with a cobot. So that means you can pick it up, put it over on a table somewhere and just clamp it on down there and you're good to go. So that's what a lot of cobots are kind of set up to be able to do that. Oh, I'm going to walk over here because we're going to have another fun example of some robots. Let's see. Are you seeing anything that looks interesting? I mean, it's like yeah, I mean, this is one of those rare cases where you can just see so many different brands and different types of examples of robots and how everything works.
Then I saw a jelly robotic. You showed me in the morning that maybe the camera can show a jelly
Oh yeah.
if it's nearby.
See the camera. See which one. Oh, okay, I'll go to agility and then I'll do one more stop off over at Archimedes. I think we want to go over and see the Archimedes drive. Okay, there's Lincoln Electric, which is really known in the area of arc welding, and they're a really big user of visual components. We're very proud to have them as a customer. So they use our software to program the welding robots that they have, and they're right next to Agility, where we're coming to right now, and we'll get a chance to see Digit. Now, this is a scaled down version of what they typically show at some of the bigger shows. But still, we will get to see Digit moving around on its own. And there is Digit. Oh, okay. So now this is a Sisyphusian task where it's constantly taking the boxes, rolling them up the mountain, and then they roll back down, and it has to do it all again, nonstop, all day long. And so, an example of interfacing with a mobile robot, we've got April tags on there that helps it to identify that that's the right one or different location tags there. So there's no ambiguity on the different location, and we get an idea of what. Okay, you see that motion right there? It looks like it's rotating its torso, but notice it pulled that trick off without actually having any torso axes. This is something we've talked about before. The redundancy in the legs allowed it to get that twisting motion of the torso without actually having torso axes. You also can see now how quickly it can rotate its legs to change position and orientation. Yep. And now see quickly like that. So that's basically the R axis that we always talk about. So this is an ARF, right? An ARF design. We get the very first one is abduction, then we get the rotation, and you see they utilize that rotation really quickly to reorient the legs 90 degrees so that it's facing the right direction. Now, this is nice. You see how low down it's able to get with its knees are not bumping into the cart. And, you know, unique hands, you know, grippers suited for this particular job, moving around. And we can see the other one is sitting over there. And we'll come around and take a look at that one. Uh, Recharging right now. And it's able to dock it, undock itself automatically, so you don't have to do it. No human intervention is required. Waiting for some instruction. Again, you see how it's rotating the torso without having any torso axes because of the redundancy in the leg. It can lean forward also if it needs to with the same trick. No need for torso axes or waist, as I think we've called it in the past. And yeah, okay, I think you saw how quick it was just able to get those legs around to where you want it to be. It used to be much slower. Remember, it used to kind of pitter patter its way around. And now it's like almost in 1.5 steps, it's there. And then we can get kind of a close up of this one while it's asleep, get an idea of what the leg mechanism looks like. And again, they use rotary axes, and you might be able to see the two control rods coming off of the different rotary axes on the leg that go down to change the ankle joint so that it can rotate down there at the ankle joint. A parallelogram kind of structure here so that the knee doesn't actually have an actuator at the knee, but the actuation from that is actually coming from a strange combination of those two different actuators that play off doing both flexion of the hip and flexion of the knee at the same time. Yeah. So that is agility and digit.
Did you see any other humanoid robotic company?
There is one other that I'm going to sort of head over. That's Real Man. Unitree is supposedly here, but I don't think they have a booth. They just have a bot walking around. And again, we can take a look at another kind of high payload robot here that's again using a parallelogram. They don't have a motor directly at the third axis. The motor you see there is probably the one that is controlling the fourth axis that's rotating right now. So they kind of set it up that way. And that's what's going on with the parallelogram. And let me see, are they using a ball screw down there as well? I don't think so. I think that's a counterbalance that the mechanism they probably have there. Or it could potentially, could they all, uh, or, or that, oh, they might be using the ball screw to actually change the third axis. So that's what they're using to drive the third axis. Huh. So a couple of examples of linear drives being snuck back into industrial robots, where the trend had been that you wouldn't really be doing that, but I hadn't, because that black motor that we see right there on the left side, I think I'm pointing at it right there, on there. That's for the second axis, and then this parallelogram, it's being actuated by what looks to be, yeah, a linear actuator in there is probably doing that. That motor that we see, the big one there, that is for axis one. That's for removing axis one. And if you wonder what those structures are off on the side, that's for the forklift. They usually are removed after it's put on site, but because this is a trade show, they're bringing it in and out. So it's like, oh, that's the forklift to pick it up and move the robot to where you need it to go. And then we see the rotation that's kind of going on there. Or actually, oh, wait a minute. No, 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 no. Now I see what's going on. No, that's a counterbalance. Ah, yeah, they tricked us out here. They actually, I've seen this in a couple of robots. The third axis is actually mounted after it. It's not part of the parallelogram structure. This is something that's a trend with several Japanese robot companies. Only seen it on them, that they actually make the third axis. So that big axis thing had nothing to do with axis four. The axis four, we can see it's that smaller servo right there. So they have a pretty big rotary axis there. And okay, yeah. So the whole idea is when they move the structure, it keeps that. Usually, when you rotate axis two, your upper arm is going to rotate along with it. And this kind of structure means that when you're rotating axis two, the upper arm stays parallel to its current position. And that's the point of that offset. Okay, so that is not a ball screw drive. That is basically a counterbalance for the parallelogram structure. And axis two, when it rotates, changes that angle of that up there, and then you get that big actuator up there, which is the axis three. Okay, yeah. Now that I see how that's connected on there from that side, that makes sense. Yeah, I can see that's where it articulates there now. I thought it was just Kawasaki that did it, and that's why I'm seeing Nachi and say, okay. And I'd seen that a few times on some of those. So that's one way of doing it. And now what we can do is we'll head over to Real Man, and also we'll take a look at the Archimedes drive. So we can go ahead and do that. Uh,
What do you think of them?
I think it's interesting. I think it might work in some situations. So they say that they're getting the torque density down to where it's compatible to a harmonic drive for humanoids. And they're very confident they can come up with a solution that is comparable with whatever others are using right now. So yeah, and of course you can see right here, there's the visual components booth, and there's my whole team sitting around. Yep, yep, yep. And Yep, and right over here, you see if you want to buy drives, you can buy some linear drives from them. You can also buy some, rotary drives, some different examples that are here. I think this is, they were pointing this out to me. This is like a harmonic drive that you would have in there. And with a 100-to-1 gear ratio, I believe. And then you have this, basically this bearing mount that you could put on there that takes the loads that are going to be off axis. So a lot of times you might need to put that on there if you're afraid that you're going to get a lot of those twisting motions that would happen to your actuator. It helps isolate that to make sure it doesn't get transferred to the central axis. So that, an example, you take a servo and you connect it there onto what is going to be your harmonic drive gear reducer. And that's, I think, maybe 5100 to 1. I remember them telling me something like that. So yeah, so these are different kinds of drives. And again, you can see how kind of like a ball screw drive works here. Is that as you rotate that thing, things are going to move. So there'd be kind of a linear drive and other kinds of linear drives. So these are neat.
Where's Archimedes? Archimedes.
Archimedes is coming right on up. So Archimedes is right over here.
Which company did you show us? Which company did you show us lost now?
Oh, that was Taiwan Excellence. So there's several companies from Japan, from China here that are showing off different kinds of actuators and actuation strategies. And here we go. So there's the Archimedes drive. Hello, Yaron. Yeah. All right. So this is kind of what the Archimedes drive would look like. Okay. So you can see it in my hand, right? Get an idea. It basically works like a planetary gear. The carriage isn't here right now, so we can kind of see how it works. But the idea is there are the rollers that act as the planetary gears that you would normally see in a planetary drive system. The difference is, think of this as having an infinite number of, of teeth. Okay, so when you go in the limit, you get rid of the teeth, but now you don't have any teeth that break off. But you have this compressed in there very tightly that it's able to still create enough rolling friction to allow you to transfer. And what are some of the so you're able to do like 5-to-1, 10-to-1. What's the maximum numbers you're able to do for gear ratios? Do you 1 to 20 or 1 to 200? I'm not sure if it's being picked up with my mic. So a 1 to 200, and again, it comes with it. It's got very high efficiency around 90% in the energy transfer, I believe, something like. Yeah, yeah. 90 to 95%, very low noise. So you're not going to hear the kind of noise you would hear with a strain wave or harmonic drive or a planetary gear system because it's rolling on top of it. Very hardened steel, so both the same material. Because of that, the temperature range is also remarkably very good. You would think the tolerances would be so demanding it would only work within a small range, but what, like minus 20 to I think 50 Celsius. So that's, yeah, 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 yeah. Exactly. The idea. I mean, you can see how simple and elegant it is. I think this is what, about 700 grams right here. Yeah. Yep, yep. So that's an early version that they're showing here. And what we will be doing is that we'll be having a podcast with you in a little bit. So I'm just showing Marwa a little bit of what's going on. This is going to be our B-roll uh, when we get in there. And yeah, one of the demonstration units actually had to go back on the road, so we can't show that right now. But we get an idea over here of kind of what it looks like a cutaway on the inside. So again, your classic kind of sun gear that goes in here with the planets that are orbiting around it. Normally there's a carrier to keep them in place. This is not being shown here. Otherwise they would kind of roll around and bounce into each other. So you kind of have the carrier keep them around there. And then you have the outer ring. And that's how you're able to get the basically the gear ratio uh, in the reduction. The main advantage of this is that if you have too much torque, I mean, it's over torque protection. If you have a normal geared system and you have too much torque beyond the rating of it, it usually means a tooth is going to break. And as soon as you break a tooth on one of your gears, you can probably either throw it out or you're going to have to take it apart and replace the broken gear and everything else. In this case, it will just slip. And and that means it will be really good as a safety mechanism, that if you bump into something really hard, rather than having the thing break, it just slips. And of course, whatever you're hitting is not suddenly going to feel some rapid acceleration or being whacked very hard. And then this thing is in ready to go. Now, the only thing that happens, of course, is that once that thing slips, you've basically lost your calibration if you are determining your joint position based on input. So they actually measure the output. So that in the end, that's what you really want to know. You want to know where's the output position to be able to control your joints. So, so what would be you would think is a problem is actually not a problem. All right. Thank you, Yaron. I'm just going around giving like the tour of the highlights of everything. So say hello to Casper for me when he comes back. Okay. So, okay, and over here is Real Man.
So do you see potential of her Archimedes drive? You
Yeah,
see
yeah.
potential there.
Actually, I mean, there some of the concerns I had is that the unoptimized version had that felt like it might be just too heavy, especially if you need to have a lot of them in the robot. But they're confident they're bringing the mass down, and also the question will be the volume because uh, in order to get a certain torque output, you need to have either a wide diameter or a very long length. So remember, when you scale it down, you in theory have zero surface area on your gears. So how do you do that? And they have a little bit because they flatten the rollers. And if the rollers are very long, that increases the amount of surface contact, which means you can increase the torque. So the torque is either the length of the rollers or the radius of the overall system or the number of rollers. So there's many ways that they can kind of solve that problem. And they just have to make sure that they're able to come up with output torque that's being demanded in some of these applications. And they're pretty close to that, being able to do it. And maybe also with the, uh, so there's mass, they have excellent torque transparency, again, some safety features. So there's a lot of possibilities there, but they still have some obstacles to overcome. Part of it is skepticism. Actually, everyone feels it's too good to be true. So they're going through right now and trying to show that they actually can be competitive with standard harmonic drives. So this is another example here. This is the Real bot that you can see that is based on a mobile platform. The torso is able to go up and down. It can have a 7-axis arm. In this case, they set it up for 6 axes because they basically took an actuator out from there. We can see that they have vision system here and vision system there, and then standard kind of little grippers. And this is an example of an exoskeleton that you can use to teleoperate with. So that gives you very precise input of what the arm is going to do. It's very much one-to-one, whereas when you're doing it with a teleoperated or with a VR, there's some weird mapping that's going on there. It's not clear you can control the arm exactly the way that you want. In this way, it's much easier because this is a faithful kinematic reproduction of that particular arm over there. And so they're using harmonic drives that actually have a gear ratio of like 100 to 1. No, there was an example over here of them using it as like a massage bot, taking their standard cobotic arm. So they also have cobotic arms. And this one here is that even for a small arm, it's able to lift 5 kilograms, as you can see. And they're doing that using harmonic drives. Oh, and as you can see, this is the arm they're getting ready to put into a full humanoid, along with the hand. So we can kind of, and those are not tendons in there. That's all. These are mechanical hands, completely mechanical. Yeah.
Hmm. Which company is this?
This is Real Man. I know it's upside down right now, but we can see it right up there. And actually, there's several other companies that use the Real Man and have kind of white labeled it and put their own name on it. But I've seen it in a couple other booths of some people who are reselling it and using that. Yeah. Okay. And we have, let's see, and some other examples there. Now, the one concern I have is that, for these being cobots, using things like harmonic drives with because they're not back drivable. I'm really surprised when I grabbed the arm and tried to move the arm, it would not back drive because at a gear ratio like that with a harmonic drive, you just can't do it. So that's part of the reason why they're getting the strength out of it is because they have a very, very high gear ratio that allows them to do that. And that is something that is probably not going to be a good idea in a humanoid. They would have to uh, get that gear ratio back down to being under 10 to 1. You also need torque transparency. So it's more like a very precise industrial arm put in kind of a humanoid form. So I'm not sure that I would want to be near it from a safety perspective. and I'm not sure how well I'll be able to control it. But it's one of the few examples that we have here of some humanoid arms. And again, see UR just popping up somewhere. Again, Fennec robot over in someone's. Now here, what they're just showing is what you have to do for your dressing. Okay, so the biggest problem we have is how do we get all the stuff we need to get out the end of our arm. Now, if you're doing something like spot welding, you need really thick cables because spot welding requires a lot of current. So you have to have some really heavy cables to do that. You may also have other needs like for opening and closing the gun or your tip pressure, you need to have pressure lines. So you need to have air, you need to have power. You might even need to have water for cooling. So you've got all these services that you now have to run through. And you see, you've got to run it through this complex dressing package that goes on here. And this becomes part of the payload of the robot, but they drop it off behind the wrist. And so it still has to carry it a little bit, but it's not as bad as if you had a really, really heavy weld arm or spot welding gun on there. And again, you got to figure out how do I get all this stuff from the ground through all these articulations because the robot can do anything, right? And of course, this thing is designed to make sure that you don't kink the cables or bend them in it. So, the radius of curvature is intentionally designed to be very large because you don't want that. Everything is around there. So these are the things you have to think about. And this is mounted here at the very end of the arm at the 6-axis. So the 6-axis is carrying that around. When you teach this thing, you got to be careful that you don't rotate that too much because that's going to come back and self collide with the arm. So these are all things you have to think about. And that's why you simulate, because it may be that to reach a certain position, I've got to get that 6-axis back there, or I'm going to have to reteach it, or I'm going to have to rethink how I mount this on there. So a lot of times you need to simulate the whole thing just to understand how the cabling is going to work. And that's the point here. They're not really trying to show the robot moving, but the solutions that you would have to be able to do cable management, which is a big problem when you're building any sort of robotic system. Is it's not just the arm; it's what goes on the end of the arm. Another examples of being able to show interesting grippers design. Looks like it might have even been 3D printed to come up with that kind of idea to be able to pick up, bottles of a certain type. And so this is kind of an integrator with different robot brands that they tend to use and show how they're coming up with their solutions. Again, kind of an example here. That's using a vacuum gripper. You can probably hear that. Okay, so how do vacuum grippers work? They need air pressure or lack of pressure, right? You can hear that. Again, you need the cabling package because the compressor that is creating the vacuum is down there somewhere. You can't carry it out the end. It's way too heavy. And plus, it's just going to be too bulky. So you've got to figure out how do you bring that stuff in here. Now, look at the other thing they've done here is that the problem with building a pallet is the dimension of a pallet. It can be very tall, even though it might be very small this way. So the robot arm has more than enough reach in the XY to be able to pick up those boxes from here to here. The thing is, it quickly runs out of reach in the vertical. So what you do is you just add a vertical axis on here that will allow it to slowly go up and up and up and up and up. And it probably uses the same solution for each layer. So what it does when it gets ready to do another layer, it'll just translate itself, whatever the height is of that layer, and goes down and basically does the same thing. Because if you can reach it for one layer, in all the XYs, then you should be able to do it for all of them, so long as you translate it up the same amount, because basically it's the same pattern at that point. So those are some of the things you try to do to extend the axis of an arm. You turn it into a 7-axis problem now. A little bit of redundancy, so obviously it could go up several layers, but at some point you're just going to run out of reach. And usually what ends up happening is that you got plenty of reach to get the boxes here. Then you try to get that one in the corner and it's just like, just out of reach. And the way you get the reach back is you pull it up, because the work envelope of these guys is not rectangular, it's spherical. So at some point, if you're not down in the equator, you start moving up to the polar latitudes, the Arctic latitudes, it can't reach there very well. Right. Yeah. And then, okay. Mm-hmm. And again, here we go. Is guarding. So, the whole idea of going ahead and creating safety systems for being able to put the robots in here, everyone's got to consider this stuff. And again, by the time you've got your safety systems in here, the good it's a good chance that this costs as much as the robot arm itself, because the robot arms, like I say, are a commodity at this point. And the other thing is that, this would be an example of like a welding area where you might have something for, you need to have screens that are kind of set up. So like these kind of things is that I can see there's something behind there, but it screens out the ultraviolet, so I don't get arc eye from staring at it, but I can still see it. So a lot of times you need that extra kind of enclosure if you're doing arc welding. If you're not doing arc welding, you may have something else that's set up like this that you can see in. Just make sure people don't get in. Or in some cases, you have a glass solution. So these are all varieties of different kinds of solutions you come up with. And again, you're going to have a light curtain right here, which is going to tell if I walked in. Now it's not active. I don't see any robots going, but again, I don't want to embarrass myself. So I will, I will kind of stay out of that. But these are all the triggers that you try to set up to bring safety into your system. Now, if you have robots that are really safe to be around, you don't need this. And then if you don't need this, not only do you get rid of that cost, you now return a lot of footprint, a lot of area you can now start cramming other things in. So that's the problem with these systems is that they also taking away valuable floor space that could be used for other things. Uh, and then again, you get that kind of the Christmas tree lighting over there to tell you the status lighting of the cell and whether it's operational or not, whether you're allowed to go in. So there's different color codes that will mean different things depending upon the state of what's just happened and whether someone like me just walked in there like they're not supposed to. Yeah, well, I'm not sure how much more there is. I mean, there's plenty and plenty of stuff. Again, we're seeing the same things, more cobots that are showing. See, this is the thing I kind of noticed is that because the cobots are so cheap and so ubiquitous and safe enough to be around, you see them at the shows. In the old days, the robots were sometimes just sitting static like that because it was too dangerous to have them operating so close to people. So they would just sit there as a statue and not do anything. And if you did have them moving, you had to have them enclosed in a cage like this to make sure no one would get hurt at the trade show. And when UR came out with this, it was like unbelievably unheard of that, well, wait a minute, where's your safety fencing? How can you have a robot so close to all the people? And that's what they've done. And now everyone has it. So they have nothing to do with Universal or KUKA or anything. They're just showing the kind of grippers that they have here. So this is magnetic grippers for being able to pick up steel bars and stuff like that. So they're selling the end of arm solution, and they want to show that, hey, you see, it works with, ABB, with UR, with Yaskawa, anyone like that. So they have all those things. And I'm not sure what happened. I don't know if my pointing my finger did anything, but it decided to drop something there. Best thing is to abscond myself right now. Um, so again, that's the big difference is that you're seeing so many different robots in so many different places here. Oh, even using them for machining. Now, this is an interesting application for a cobot. Usually you would think of putting a much stiffer industrial arm in there. And so now, whoa, you're going ahead and doing machining. In this case, like a grinding application, which usually requires a lot of force that you have to maintain the force of the surface. Now, sometimes maybe that's good because you don't want to overforce. So because they have a force torque sensor, you can make sure it does not apply too much force. And if you've got like a strange shaped part, a lot of times you can go around there and it will get that force feedback and use that to stand off if it has to or push a little bit harder if it needs to. So that's like probably the reason they're using a cobot for it is they're really good at the force feedback, force torque feedback. Again, it's just another example of a SCARA robot. They're everywhere. They are everywhere. Huh. So they do grinding solutions over there. So yeah, so everyone's showing solutions, and they're showing the solutions live, which is impressive. Again, 20 years ago, you would not have seen it to this level. Now here, that's also one of the bigger players is Staubli. And Staubli is a Swiss company, but this robot has a very interesting pedigree because they ended up buying a company called Westinghouse Unimation, and Westinghouse is the one that bought out Unimation, and Unimation is the company that Joseph Engelberger founded. So the very first industrial robot was a Unimate robot. And then they did really well, and then like all big companies are doing really well. They maybe get a little bit complacent, and then they lost out to like ABB and Fanuc and Kuka and others came in. So eventually, Stoibli, which was actually a textile manufacturer, or they made textile equipment, bought them. My goodness, I'm trying to remember when. Might have been 25, 30 years ago. So it's been a while, and rebranded them. So this is kind of a derivation of one of the older, as you see, the TX, which grew up from the Puma robot. So the Unimation, the famous Puma robot, and these are some derivations of it. And Stoibli has made these things extremely precise. And so some of their application space is a little bit different than the other robots, but you see them like, in clean room and very precise pick and place kind of applications. So they're quite popular there. And so, yeah, I think it's kind of appropriate to make sure we bring them in because of the pedigree of these bots, going all the way back to the very first bot that Joe Engelberger put, I think it was the GM plant in Trenton, New Jersey in 1961 in a forging application. So, yeah, industrial robots.
How many
What we
floors?
have to see.
How many floors this show? Only one floor. The show,
Pardon?
the Automate show. How many floors? It's just this the main show one floor or multiple floors?
Yeah, well, there is a second. There's a second floor down below, which has a lot of smaller booths. It's not really any robots. There's like a student competition going on there, robotics, and showing some other things. But it's one big hall. It's a little bit smaller when it's in Detroit, but when it goes to Chicago, it gets a bit bigger because McCormick Hall is huge. They can have like 3 trade shows simultaneously going on at McCormick. It's so big. Whereas down here at the Huntington Place, it's a little bit different. And so Fanuc usually has like a monster booth at these robot show, but there's only so much space here. But when you go to the show when it's probably in Chicago, the Fanuc booth might be 4 times that size, and that's where they have the room to bring their really large robot in. The Godzilla robot, you'll see that there, and also at Automate in Munich. It's a pretty large venue as well, and Fanuc has like an enormous presence there as well, where they bring everything in. So that's only 4 weeks away. Yeah, it's maybe 5 weeks away. So for a lot of these robot companies, it's like, man, 2 major trade shows so close together. We have to, limited budget, how much we're going to bring out, and the Automatica seems to be more of a worldwide kind of event, whereas this tends to be more North American.
I think Automatica much bigger than Automate.
Oh,
Much.
it'd be much bigger, much big, oh, much bigger. Yeah, we'll see the same robots there and more, no doubt about it. Now, here's an interesting example. How do you sell the problem of being able to pick up um, packages like this and trying to come up with a universal gripper that's able to work on all sorts of things, because suction grippers are good with certain kinds of materials and really bad with others. And when you're in a sorting facility, like we have at FedEx or DHL or UPS, you have no idea what the packages are going to be. So Amazon famously chose certain box sizes and types to make it easier for them, but if you're trying to do the U.S. mail, people will throw whatever they want in there. So this is an interesting approach to a vacuum gripper that works pretty well. Every now and then there'll be one that it might not be able to pick up because it's a really odd shape, but they are showing. You see, you didn't pick that one up for some reason, and maybe okay, second try. I tried it the second time, and sometimes it can be as simple as like the texture of the surface is different. It's a shiny surface or not shiny. Boxes can be really bad when it comes to vacuum. A lot of times the boxes let too much air in, so that's why you'll see a lot of boxes that are almost like sealed on the outside intentionally to make it easier because it likes gripping saran wrap and stuff like that. So if you wrap your box with a lot of tape, usually it will work well. So yeah, it's an example of trying to come up. It's not about the robot. Like I say, the robot's a commodity. You can buy any robot arm of about that size and that payload capability that you need. The engineering is right there in that end of arm tooling, which may be a very unique application. So if you can't find something like that out in the market, and you can now, but in the old days it was really hard. You had to build them yourself, and it costs a lot more for you to fabricate one version of that, whereas they're producing tens of thousands of these a year, so their production costs are a lot less than you doing quantity one. We have to do all the design and testing and validation. So yeah, that's Automate.
Wow. I know you told me the show ending tomorrow, right? Tomorrow's the last day.
Yeah, it ends early at 3 o'clock. If I see anything else interesting, I'll make sure to go ahead and take a look at it. Okay, here's a good example of putting a robot actually on an AMR to take care of certain tasks. So you imagine it's like, okay, I'm going to pick up a bunch of parts here, and after I pick up all these parts, I have to deliver them somewhere. So when I deliver them to the other end, who's going to unpack this? One way of doing it is you could have a fixed arm right here that's like loading this thing, and a fixed arm on the other side that's taking them off. But one of the advantages of a mobile robot is it gives you a seventh axis for free. It actually allows you to drive this thing because there's no way the robot can reach all the bins. Maybe from the central location, it might be able to do it. But in order for it to get over there, it's going to have to translate down, and then it can pick it up. And then when it's done, it goes and delivers it somewhere else. So this is an example where you may decide it makes sense to put the arm on here. And I have like, if you remember a few weeks ago, I posted a video I did kind of looking at that exactly. You know, these situations like when does it make sense to put a robot on there or not put it on there? And it comes down to you have to look at the application very closely. So it's not that this is a bad idea. In some cases, this is a very good idea, and it's the right solution for that case. In other cases, it may not be a good idea because let's say I'm transporting lots of the same stuff. Rather than picking off of here, the same boxes are coming down and need to be delivered to different locations. And it's a lot of volume coming through there. So I need a lot of AMRs picking up and delivering, moving around there. You want me to put an arm in every one of those? That gets costly. So maybe it makes sense to have a fixed arm at one of those locations that's picking it up and dropping it onto those AMRs as necessary. So again, it depends upon exactly how the flow is, whether to put an arm on there or not. But what I want everyone to see is that you're not excluded from being able to mount your arm on your AMR. And it's actually a very popular solution in many cases because it actually does fit the situation really well. Um, And again, this is an example that if you need to do spot welding, a spot welding gun is really big and heavy. So you need to have a robot that's up to the task and big enough to be able to reach around different parts of the automobile body. Well, in this case, you're not doing it on the full automobile body. So it's actually a slightly smaller robot than you might see on there. What this is doing is this is like a sub-assembly cell where you're building some of the smaller parts that are going to go on the car later on. So over here, you got the robot. It's just showing off, right now. And then we come over and perform some of these welds while you have another robot that's okay. So basically, it was bored waiting for this guy to put together the assembly. And then once it's all done, that robot's probably going to pick it off and put it off in another bin. So you've got dunnage over here you've got to pick out of. Okay, here's the little pieces. See all the little pieces that are there? It's going to pick up all those little pieces and it's going to drop them onto that turntable. So while the robot is assembling this piece here, doing whatever it has to put those parts on there, the other robot is welding. So you see that's the finished piece. It'll go ahead, drop it in the dunnage. So, you got to make sure the robot has the right reach for that dunnage. It's a little bit tricky. And then it kind of comes back, and now it's going to build the next one. So it's going to go over here. Well, I guess it dropped that piece in there, but it's going to take like this unfinished pieces. Let's say the raw material over on the left side. It'll pick that up. It'll drop it in there. Then it'll probably drop that part on there. And the idea is that part is then supposed to be welded by the robot on the other side. And it just keeps turning around and turning around until it's done. You want to pick it up, bring it over in the turntable. You've got to have all the handshakes between the two robots that they agree that, okay, you're done welding, I'm done loading the part, we go ahead and advance the turntable. So that gets on there. Notice that gripper could pick up two parts simultaneously. And now, whoop, it's all done. And the show is about to end. So they're getting ready to turn everything down because people just can't wait to get out of here. It's been a long day. So, yeah. So, and again, look how the turntable is designed to make the part face the robot a bit more easily so it can reach all those points. And now that one's unloading it. And obviously, it's unloading it two parts at a time because they're not really welding here at the trade show. But normally, those pieces will be welded and then dropped in there. So, okay, and we can see right up there the family of cobots that Fanuc has come up with. Now, there is an argument about the proper pronunciation of Fanuc. There's some people will say Fanuc.
Is it German?
So, no, it's Japanese. It actually it's an acronym, and it came out of like the NC. They originally did like NC, so it's something about like numerical control. So I think it was like Fujitsu automation and numerical control, something like that. You'd have to look it up. Don't quote me on that, but it is, and no one's quite sure how you pronounce it, Fanuc or Faduk. I think most people say Fanuc, but then you'll hear some other people that say Fanuc. And then I have a third pronunciation, and that is Fanuc. And you remember that because it rhymes with Canuck, which is also um, slang for someone who's Canadian.
Yeah.
So you can come up with any sort of any sort of pronunciation that you wish. All right, so that was in the show. As you can see, everyone is eager to get out of here. Uh,
But I wish I was with
and
you in this event, but hopefully, yeah.
we'll be at the next one. This will be a warm up. This is like an appetizer for the next one, and hopefully for the audience, they will get something out of this. So I don't know, they'll learn a thing or two. Yeah, yeah. Actually, I had someone come up to me that's working on one of the booths that liked the singularity content and said it
Oh,
was like really informative. So
you have a lot of
yeah.
fans, a lot of fans, cause
Yeah. So he liked the visualization tool and thought that it was a really clever idea and gave them a lot more insights. And they're thinking, that might be a not good idea to put in our controller because they're developing controllers. Yeah. So okay. So I guess I got to sign off right now. We're back at the booth.
yes, maybe you're saying goodbye and saying
Yep.
goodbye in the camera.
Yep. Will do. Oh, I didn't even have to do it this way. So yeah. Cheers.
Okay, see you later. Okay,
Yep. Bye. Yep.
bye.